Hey everybody, welcome back. This is CHEM300 and we're wrapping up chapter 6 today with talking about how to calculate molecular formulas for a compound. So our goals in this section are to understand the difference between empirical formulas and molecular formulas, and then to be able to determine the molecular formula from percent composition and molar mass of a compound. So the figure that I have on this first slide shows one of the key concepts of this section. Up top is the molecular formula for glucose, C6H12O6. And then if we divide everything in that formula by 6, so the 6 moles of carbon divided by 6, 12 moles of hydrogen, and the 6 moles of oxygen, we get CH2O, which is the empirical formula for glucose. So a difference between molecular formulas and empirical formulas is that the empirical formula is the lowest whole number ratio of atoms in a compound. But molecular formulas may not necessarily be the lowest whole number ratio. This is the actual ratio of atoms in a compound, how it's actually found as a molecule out in nature. So we're going to learn today how to go from empirical formulas to molecular formulas and molecular formulas to empirical formulas. And they're always different by some whole number amount. Either you're dividing by a whole number to turn molecular formula into an empirical formula, or you're multiplying by a whole number to turn an empirical formula into a molecular formula. So let's compare and contrast these a little bit. So empirical formulas give the lowest whole number ratio of atoms of each element in a compound. So again, if we use glucose as an example, the empirical formula for glucose is CH2O. Those are the lowest whole number ratios for the elements carbon, hydrogen, and oxygen contained in glucose. Whereas the molecular formula, that gives the kind and number of atoms of each element that are actually present in the molecular compound. So this is how glucose is actually found as C6H12O6. So molecular formulas may or may not be the lowest whole number ratios. In the case of glucose, it's not. But they're always going to be a whole number ratio of the empirical formula. So here the difference is 6. So you divide by 6 to go from the molecular formula to the empirical formula, divide by 6, and to go the other way, you multiply by 6. So we'll call this N. The multiplier or divisor between the empirical and molecular formula is 6. There's a 6 times difference between the two. So if we can calculate the empirical formula, which we know how to do from mass percent composition data, and we can figure out what N is, what the difference is, the multiple, then we can convert empirical formulas into molecular formulas. And that's what we're going to be learning how to do in this section. So to convert between the empirical and the molecular formula, it's always going to be a whole number ratio. So you're going to take the empirical formula, like CH2O, and multiply it by a whole number. And in the glucose example, that was 6. And we got C6H12O6 glucose. We can rearrange this equation to solve for N. So if you take the molecular formula divided by the empirical formula, C6H12O6 divided by CH2O, we get that there's a ratio difference of 6 between each of these. 6 divided by 1 is 6, 12 divided by 2 is 6, and again, 6 over 1 is 6. So N, the multiplier between the empirical formula and the molecular formula for glucose, is 6. So let's do a little practice. Let's determine the molecular formula for a compound that has an empirical formula of C11H16O. And we know that the N for this compound's empirical formula is 2. So to convert from the empirical formula to the molecular formula, we're going to multiply everything by N. So we have C11H16O. And we're going to multiply everything by 2. So we get C22H32O2. And this is the molecular formula. Empirical formula over here. And for anyone interested why I picked this molecule, it's not just some random molecule. This is what's known as DHA, docosahexaenoic acid. It's the fatty acid found in fish oil that is very good for human health. It's a polyunsaturated fatty acid. So if you take any sort of omega-3 or fish oil supplements, what you're really paying the big bucks for is this DHA molecule, docosahexaenoic acid. Okay, let's do another practice. So let's solve for N, that whole number multiplier, given the molecular formula and the empirical formula. So here we have a molecular formula of C2H4O2, C2H4O2, an empirical formula of CH2O. So again, to rearrange this equation, we're going to take our molecular formula, divide it by our empirical formula, and that's going to give us N. So we just rearrange that to solve for N. So if we look at the ratios of the carbon atoms is 2 on top and 1 on the bottom. And for hydrogens, it's 4/2, and for oxygens, it's 2/1. So each of those are a ratio of 2. So N equals 2. So again, just to recap, N is always going to be a whole number. It's what you multiply the empirical formula by to give you the actual molecular formula. So again, the empirical formulas are always the lowest whole number ratios of atoms. But the lowest whole number ratio of atoms isn't necessarily how a molecule is found in nature. So to calculate its molecular formula, the actual numbers of each type of atom, we need to multiply the empirical formula by N. How about if N equals 1? If N equals 1, then you have a situation where your empirical formula and molecular formula are the same. And that sometimes happens. So because chemical formulas are the ratios of the moles of each type of atom in a chemical compound, we can use the molar masses of these compounds to also figure out the value of N, the multiplier between the empirical formula and the molecular formula. So if we find the molar mass of the molecular formula, say C6H12O6 molar mass, and we calculate the molar mass of the empirical formula, CH2O, and we divide those two molar masses, the molar mass of the molecular formula divided by the molar mass of the empirical formula, we're going to end up with the same N. So this is what we're going to be doing when we get to solving for the molecular formula for compounds. We already know how to calculate empirical formula from elemental analysis data, from mass percent data. And so we can calculate the empirical formula, and we could arrive at something like this, CH2O. And now that we know the formula, we could calculate its molar mass, and I'll do that quick. We have 12.01 plus 2.02 plus 16, so 30.03 grams per mole. And if we know the molar mass of our actual compound, when we divide these two, we're going to get the value of N, which means we could take our empirical formula, which we just solved for, and multiply it by N to get the final formula of our molecular compound. So let's calculate the molar mass of glucose quick and check this out. So we have 12.01 times 6 plus 1.01 times 12 plus 16 times 6. And I get 180.16 grams per mole. So 180.16 divided by 30.03 will give us N. And I get 6 exactly. So what this means is that to go from our formula for the empirical formula of this compound, I have to multiply everything by 6. I just solved for N. And now to convert from the empirical formula to the molecular formula, I multiply everything in the empirical formula by 6. So again, we know how to calculate empirical formulas from percent composition data. And if we know the molar mass of our molecular compound, then we can divide the two masses to get our N value, and then you multiply the empirical formula by N to get your molecular formula. So let's do some example problems. So let's find the molecular formula for butadiene. Butadiene empirical formula is C2H3O, and the molar mass is 86.03 grams per mole. So we're going to use this N equals molar mass of the molecular compound or molecular formula divided by the molar mass of the empirical formula and so they gave us the molar mass of the compounds, the actual mass of the ratios of the atoms, so 86.03 grams per mole. And now we have to calculate the molar mass of the empirical formula. So we know our empirical formula from the problem is C2H3O. So we have 12.01 times 2 plus 1.01 times 3 plus 16. 2 atoms of carbon, 3 atoms of hydrogen, and 1 atom of oxygen in the empirical formula. So the molar mass of that empirical formula, 12.01 times I end up getting 43.05 grams per mole. So that goes here. And now when we divide these two, 86.03 divided by 43.05, I get 1.998, and it keeps filling up my calculator. So that's close enough to 2 to round it to 2. So our N equals 2. So to find the molecular formula, now that we know our N value, we have to multiply our empirical formula by N. Molecular formula equals empirical formula times N. So we're going to have 2 times C2H3O. So 2 times 2 gives us C4. 2 times 3 gives us H6, and then O2. So again, if you know your empirical formula, you can calculate its molar mass. And if we know the molar mass of how the compound's actually found, then when you divide those two, it gives you the multiplier to go from empirical formula to molecular formula. And we were given the empirical formula, so we multiplied the empirical formula by N. In order to obtain our molecular formula. And this is just showing the key equations that we used. We used molar mass of the molecular formula divided by molar mass of the empirical formula will give us our N. And then we multiply our empirical formula by N to give us the final molecular formula. Let's do one now where we determine the molecular formula by first determining the empirical formula and then multiplying by that N value to get the final molecular formula. So aldrin is an insecticide that was commonly used in soil fields until it was banned in many countries. It's found to consist of 39.50% carbon, 2.21% hydrogen, and 58.29% chlorine. Its molar mass is 364.84 grams per mole. So this is its molecular formula molar mass, how it's actually found. So using this information, determine the molecular formula for aldrin. So we're going to open this up on a whiteboard to give us a little bit more space to solve this problem. Okay, so we've got mass percent data. And so we're going to use that mass percent data to first calculate the empirical formula. mass percent data to empirical formula. So we've got 39.50% carbon. And then if we assume that we have a 100-gram sample, that gives us 39.50 grams of carbon. We're going to do the same thing with the hydrogen. We have 2.21% hydrogen by mass. We're going to assume that we have a 100-gram sample. So 2.21% of 100 grams is 2.21 grams of hydrogen. Last but not least, same thing for chlorine. We have 58.29% chlorine. We're going to, again, assume that we have a 100-gram sample. And so 58.29% of 100 grams is 58.29 grams of chlorine. Now for each of these, we're going to take their masses and turn them into moles of each so we can write the pseudo formula and eventually end up at our empirical formula. I'm just going to move these down a little bit to give myself just a little bit more room here for each of these. There we go. Okay, so let's do carbon first. 39.50 grams of carbon. We want to convert that to moles. So for every 1 mole of carbon, that weighs 12.01 grams. So we get 3.2889 moles of carbon, and I held on to an extra sig fig there. I should have stopped at 4, but I kept 5 just to make sure I don't make any rounding errors later. Okay, let's do the same thing with hydrogen. For every 1 mole of hydrogen, that weighs 1.01 grams. So 2.21 divided by 1.01 gives me 2.188 moles of hydrogen. And same thing with my sig figs. I should have rounded that to 3 if that was the end of my calculation, but since it's an intermediary step, I want to keep an extra sig fig to make sure that the rounding doesn't mess up my final answer. Last but not least, chlorine. 1 mole of chlorine weighs 35.45 grams. So I get 1.6443 moles of chlorine. And same thing with the sig figs. I'm going to keep 1 extra sig fig. We should have 4, but I'm going to hang on to an extra one to make sure I don't mess anything up due to early rounding. So I'm going to write my pseudo formula. I get C3.2889, H 2.188, Cl 1.6443. So I'm going to divide everything by the smallest. So divide everything by 1.6443. So 3.2889 moles of carbon divided by 1.6443 gives me C 2.0001. 4 sig figs. It's going to be rounded to 2 eventually. I check out my hydrogen, 2.188 divided by 1.6443 gives me 1.3307. And that should have 4 sigs if I was rounding, but I'm not yet. And then my chlorine. ends up just having 1 mole of that because we divided it by itself, so Cl. So I could round the carbons to 2. They're close enough to 2 to be rounded to a whole number, but my hydrogens are not close enough to 1 or 2 to be rounded to either of those whole numbers. So this is where I need to multiply everything through to get all of my mole ratios close enough to whole numbers. So since it's ending in 0.33, I'm going to multiply by 3. So I'm going to multiply everything by 3, because anything we do to one of the mole ratios, we have to do to all of them. And so at that point, I get, I write it a little bit smaller so I don't run out of space. I get C6H 1.3307 times 3 H4Cl3. 2 times 3 gave me my 6 moles of carbon. 1.3307 times 3 was 3.9921, so that was close enough to 4 to round it to 4. And then Cl times 3 gives me 3 chlorines. Okay, so this is my empirical formula that I just solved for. Empirical formula. So now that I have my empirical formula, I can calculate the molar mass of this empirical formula. And what we're going to do to solve the last part of the problem is we're going to take the molar mass of the molecular formula divided by the molar mass of the empirical formula to give us our N value. And then once we know N, we're going to multiply everything in the empirical formula by N to get the molecular formula. So I'm given my molar mass for the molecular formula. It's 364.884. So I can put that in up top. 364.884 grams per mole. And for my empirical formula, I'm going to add up the mass of 6 carbons plus 4 hydrogens plus 3 chlorines. So 12.01 times 6 plus 1.01 times 4 plus 35.45 times 3 gives me a empirical formula mass of 182.45 grams per mole. So now when I divide these two, 364.884 divided by 182.45, I get 1.99, which is 2. Close enough to 2 to round to 2. So final step is to take our empirical formula and multiply it by our value of N. So 2 times C6 H4Cl3 gives me C12 H8Cl6. And that's the final molecular formula. Okay, so that was a big problem. It covered a lot of this material from part 2 of chapter 6. We took percent composition data. We converted it into mass data by assuming that we had 100 grams of sample. We then found the moles of each element in the compound. Using those moles, we set up a pseudo formula that gives us the mole ratios, but it's not whole numbers yet. So to get it to whole numbers, we divide by the smallest number of moles. And it still wasn't whole numbers at that point. So then we had to multiply, in this case by 3. And then all the mole ratios ended up close enough to whole numbers within 0.1 of a whole number to round to whole numbers. And that's how we ended up with our empirical formula down here of C6H4Cl3. We then had to use the relationship between molecular formula and empirical formulas to calculate the multiplier. molecular formulas and empirical formulas will always be related by a whole number value, a multiplier. So we can take the molar mass of the molecular formula, which we were given in the problem as 364.884 grams per mole, and divide it by the molar mass from the empirical formula. We calculated the molar mass of the empirical formula by taking the mass of 6 carbons plus the mass of 4 hydrogens plus the mass of 3 chlorines and adding them all up. When we divided those two, we get the N value, the multiplier value. It was 2. So that means we have to take our empirical formula, multiply it by 2 to get our final molecular formula. Okay, I'm going to pause here for just a second. So if there's anything you need to write down, you can get it, or you can always pause the video. And then let's jump back to PowerPoint. Okay, so that is the end of chapter 6. We learned about what a mole is using Avogadro's number and molar mass as conversion factors. We learned also about using chemical formulas as conversion factors. Then we learned about percent composition, how to calculate percent composition for a compound based on mass data, doing elemental analysis, as well as how to calculate percent composition based on the chemical formula. Once you have percent composition data, you can use that to calculate the empirical formula for a compound. And if you know the empirical formula and you know the molar mass of the molecular compound, how it's actually found, you can calculate the molecular formula from the empirical formula using that N multiplier, which is what we just did. So our chemistry and everyday life exercise for the end of chapter 6 is to look at mass percent from food nutrition labels. So nutrition labels commonly list information about food molecules and micronutrients important in human health, like fats and carbohydrates and protein and vitamins like vitamin C and minerals and micronutrients like iron and calcium. Nutrition labels list this information in terms of the mass of the food molecule or micronutrient contained in one serving. So they list them in terms of mass. So we can get some practice with mass conversions by looking at some food labels for some items you might already have in your home. So what I want you to do is use the food label to look up the mass of a food molecule or micronutrient per one serving. They always list this in grams, and then you always know what weight one serving is. So you can come up with the mass percent for that food molecule or micronutrient. Then use that as a conversion factor to calculate how much of that food molecule or micronutrient you would ingest if you ate the whole package of food. Does your value agree with what's listed on the package label? So I'm going to show you an example on the next slide. So I love cookies. They're probably one of my weakest kind of food things I go for. And I especially love Girl Scout cookies. So these are Caramel Delights, the nutrition label, one of my favorite cookies. So I wanted to look up what's the mass percent of saturated fat in one serving of Caramel Delights. So I checked out the food label. A copy of it is up here. And I looked up saturated fat here. So there's 5 grams of saturated fat per serving. And nutrition labels in the US are always listed amount per serving. So one serving is 2 cookies, which is 28 grams. So my mass percent of saturated fat equals 5 grams of fat for every 28 grams of cookies if I'm doing it per serving, times 100. So 17.85%. And food labels are terrible with sig figs. Look, they only give you 1 sig fig here, so we should really only end up with 1 sig fig here. 20% by mass, saturated fat. It's a lot of saturated fat. I really didn't enjoy this once I saw how much it was. I probably won't eat as many Caramel Delights. So Caramel Delights, 20% by mass saturated fat in 1 serving. That's part A. What's the mass percent of saturated fat in 1 serving? We could use this now as a conversion factor to determine the amount of saturated fat I'd get if I ate the whole box of cookies. So again, like I said, I started down this path and then I wish I hadn't because it's making me rethink my cookie eating habits. So we can use percent composition as a conversion factor. So 20% saturated fat by mass means that there's 20 grams of saturated fat for every 100 grams of cookies. So if a serving is 28 grams and there's 8 per container, we can figure out how many grams of cookies are in a whole container. So 28 grams per serving times 8 servings per box. That will give us our grams of cookies per box times 20 grams of saturated fat per 100 grams of cookies. This is grams of cookies. So if we check our units here, servings cancels out, grams of cookies cancel out, we end up with saturated fat per box. Okay, so 28 grams of cookies times 8 servings times 20 grams of saturated fat divided by 100 gives me 44.8 grams of saturated fat per box. If anybody knows how much saturated fat is recommended per day, that's over 2 times the daily recommended amount. So I'm going to try to abstain from eating an entire box of Caramel Delights in one day, which I certainly have in my lifetime, because it would be about 2.5 times my daily recommended amount of saturated fat. So try this out at home. It's just a kind of a fun way to learn a little bit about your food and what you're eating every day, and get some practice with these mass percent conversions. Hope you have fun. Let me know how it goes. Thanks, everybody. I'll see you next time.